Our next speaker has been involved in the Belgian Geological disposal programme for almost a decade, where he coordinated the R&D on feasibility and engineering of disposal's content. Since 2015, he's worked in the disposal unit in the IAEA, supporting member states to find safe and cost-effective disposal of radioactive waste, which sounds really easy. And please welcome Dr. Philippe Van Marcke.
Okay, thank you. So as it was mentioned, I work for the International Atomic Energy Agency, in short IAEA, and in the same way as it's important for the NDA to listen to its stakeholders, it's important for the IAEA to listen to what goes on in the member states. So it's a great opportunity for me to listen to what's happening in the UK, so I thank the NDA for inviting me to this event. Okay, let me first explain a little bit what the IAEA is, and to do that we need to go back some 80 years to the discovery of nuclear fission, because with that discovery, and in particular with the bombs on Hiroshima and Nagasaki, scientists and politicians realized the enormous power that is created by a fission reaction. And they also realized that this power could be used for the good or for the bad. And that led US President Dwight Eisenhower deliver in 1953 a speech at the UN General Assembly in New York. And in his speech that was titled Atoms for Peace, Eisenhower advocated the creation of an atomic energy agency to promote the peaceful uses of nuclear energy while preventing its use for any military purposes. And that agency was created 4 years later, and that is now the IAEA. The IAEA exists today for 60 years, and I think most people will know it from the weapons inspections in Iraq some 15 years ago, or more recently from the negotiations with Iran on their nuclear program. But the IAEA is more than a nuclear watchdog preventing the spread of nuclear weapons. We also support countries in using nuclear technologies to achieve the Sustainable Development Goals adopted by the United Nations in 2015. These goals cover areas such as human health, poverty, clean water, energy, climate change, etc. And that is why our Director General, Mr. Yukiya Amano, prefers to refer to our mandate, which was originally summarized as Atoms for Peace after US President Dwight Eisenhower's speech. Mr. Amano prefers to now refer to it as Atoms for Peace and Development. So what do we specifically do? Well, you can break down our work into the following 3 pillars. The first one is the IAEA in its role as a nuclear watchdog. We implement safeguards in countries to verify that all nuclear materials and activities are used for peaceful purposes only. I've given the example already of the IAEA doing nuclear verification in Iraq and Iran. The second pillar is safety and security, because of course if you're going to use nuclear technologies, it is of the utmost importance that you're going to put in place the necessary safety and security measures. Now, these are national responsibilities, but the IAEA provides a forum where countries can exchange information and expertise, and where they can develop agreed safety and security standards. And the last pillar is the one I already mentioned. So we support countries in using nuclear science and technology to achieve their development goals. One example is the involvement of the IAEA last year in fighting the Zika virus in Latin America, by using nuclear technologies to sterilize mosquitoes. We are with more than 2,500 staff members from over 100 countries. 168 countries are member of the IAEA. Our headquarters are in Vienna, but we also have regional offices and laboratories in Cybersdorf, that's also in Austria, Monaco, Geneva, New York, Toronto, and Tokyo. Now, something that all our member states have is radioactive waste. There are a whole range of possible nuclear activities, not just nuclear power, as it was mentioned by the previous speakers. And some countries do have nuclear power. They're shown here in red. Other ones do not have nuclear power plants, but they have research reactors. You can see them here in purple. And the ones that do not have nuclear power or research reactor, they use radioactive sources, for example, in cancer therapy machines. Now, also these sources, after a certain amount of time, they become disused, but they're still hazardous, and they are actually radioactive waste. So all our member states, without any exception, has to deal with radioactive waste. And in the section where I work in, that's the waste technology section, there we support these countries in managing their waste. Now you can break down radioactive waste management very schematically and roughly in the following steps. At the very beginning, you're going to try to minimize the amount or the activity of the waste. For example, spent fuel reprocessing is a way of doing it. You're going to recover the fissionable plutonium and uranium from the spent fuel. In a second step, you're going to treat the waste. And by waste treatment, you're going to actually change the characteristics of the waste so that its further management becomes safer or cheaper. For example, you might decide to remove certain difficult to manage radionuclides from the waste. You might change the composition of the waste, or you might reduce its volume. That's what you can see on the second picture to your left. You're going to compact the waste, or you can also incinerate it. You see a picture below that one of a waste incinerator. After that waste treatment, you're going to condition and package it. And by conditioning it, you're going to put it in a form that makes it suitable to further handle, transport, store, or dispose of the waste. Two examples here. So you can vitrify the waste. Then you kind of immobilize the waste in a glass matrix. That's the black material you see there, and that is then packaged in a steel container. Another example is that you put the waste in a steel drum and you fill it up with cement. That's called cementation of the waste. So in that way, you get the waste in a package in a form that's relatively easy or suitable to further handle the waste. Now, all these waste will eventually have to end up in a disposal facility. But very often, and that's also what Professor Bloos referred to, at the time the waste is conditioned, a disposal facility is not available. So as an interim measure, you're going to first store the waste, you're going to first put it in a storage facility until a disposal facility becomes available. Now, storage of the waste cannot be a final solution for your waste. And that's because you have to keep in mind that these wastes remain hazardous for centuries, to thousands to even hundreds of thousands of years. Storage requires active safety measures. You have to actually secure storage facilities, you have to inspect them, you have to maintain them, and after a couple of decades, you're probably going to have to decide to upgrade these facilities. Now, that active management of the waste that you still continuously need to do for a storage facility, that can become very expensive over these long timescales that I just mentioned. Secondly, they put the burden of actively managing these waste onto future generations. And we heard it already. It's an ethical principle in radioactive waste management that we have had the benefits from the activities generating the waste. So it's only fair that we also deal with this waste and do not keep postponing that burden onto generations and generations after us. There's a final reason, or a third reason, better said, why storage could not be a final solution for radioactive waste. That's because political, societal, and environmental conditions are not stable over timescales of several centuries. We cannot guarantee that future societies will be committed or will be capable of actively managing these wastes. Maybe they don't have the willingness to do so. Maybe they don't have the capacity or the resources to keep taking care of these wastes. Example of environmental conditions, well, over timescales of several centuries, we need to take account of climate changes, sea level rises, maybe more intensive floodings, erosion phenomena, etc. That is why the only safe and effective long-term solution for radioactive waste is disposal. And disposal facilities are facilities that are designed to provide passive safety. And that is the crucial difference between storage and disposal. Once the disposal facility is closed, you can walk away and it will be a safe situation. Or at least the facility will be designed to give you a safe situation. That does not mean that you cannot decide to inspect or secure the site or monitor it. You can still do that, but the safety will not rely on these type of measures. Now, different types of waste will require different disposal solutions. So let's first have a look at low and intermediate level disposal. This is quite routinely done all over the world today. And you can see here examples of disposal facilities for low and intermediate level waste that are operated today. In the top row, you can see trench type disposal facilities. These are often used for very low level to low level waste and mostly in very dry regions. I know France is not a dry region, but there they have a capping over that facility. In the second row, you can see more engineered, more robust disposal structures. These are often concrete bunkers that are filled by the waste packages, and at the very end they are capped by an impermeable layer to avoid water infiltration. And at the bottom row you can see facilities that are constructed underground and where they have disposed of the low and intermediate level waste. To the left you can see one in Germany that is an abandoned potassium mine in Morsleben that they now use to dispose of their wastes. Now for high level and long-lived waste, including spent fuel, these wastes need to be isolated from the biosphere for tens to even hundreds of thousands of years. And it's not possible to get this level of isolation and containment by surface disposal facilities. Over such timescales, you have to take account of ice ages, and you cannot design a surface disposal facility that can resist the power of a glacier. So for the disposal of these wastes, we need to look for an environment that remains stable over such long timescales. Basically, we need to look for an environment that is geologically stable. And those environments we find deeply underground. And you can see here an example from Dunaroba in Italy, where they had a clay quarry in the 1970s. And while they were excavating this clay quarry, they uncovered these 2 million year old trunks of sequoia trees. So this is just an example that once things get buried, they will not make part anymore of the surface. They can be, not necessarily they will be, but they can be preserved for very long time scales. And now before any one of you jumps up in anger that I'm a fabricator of fake news, I made this newspaper article, that's true, to look the slide a little bit more interesting. But the story itself is kind of true. My boss emphasized that I should make that clear, that I didn't do that. So, okay, so we call the disposal of waste in a geologically stable environment. We call that geological disposal. And here you can see some examples of geological disposal concepts. The first one is in Finland. That is a repository at a depth of 500 meters in crystalline rock, in granite. The second one is the one that Professor Blower already showed in Bure. That's in France. That's also at a depth of 500 meters, but that's one in clay. The other one is in Gorleben, that we also have seen in the previous presentation. There, the repository, they plan to build it at a depth of 800 meters in a salt formation. And the last example is the Yucca Mountain project in the United States, where the intention was to dispose of the waste 600 meters below surface in volcanic rock. Now, these concepts are underpinned by decades of R&D, and I think it's a fair and correct statement to say that from a scientific and technical point of view, these are very mature concepts. A lot of R&D was done to understand and characterize all the processes that happen in these facilities and in the host rock around it. As several countries have constructed underground research facilities to do in situ research in these geological formations. You can see one example there is the Monterey facility in Switzerland, and another big chunk of R&D was done to demonstrate that we can actually construct, operate and close such facilities. In Germany, they were confronted with the engineering challenge, and it is quite a significant engineering challenge to lower 85-ton heavy waste packages from the surface to that repository 800 meters below. So what they did was they actually constructed this facility on a 1-to-1 scale and significantly tested it. Another example is here the copper canister that you can see that they plan to use in Sweden and Finland. Well, they actually manufactured several of those canisters and in particular tested if they could weld that lid onto that cylinder. So where are these concepts in terms of being implemented? Well, Finland, they received a license to construct this facility last year, and in France they plan to submit such a license application to their regulator in the coming years. Now the examples I've given from Germany and the United States, they have been stopped. And that's not because these were considered as unsafe or not feasible to implement. They were stopped because of political and public protest. Because of course it's very fine that these concepts are becoming technically and scientifically mature, but you still need to look for a site to implement these concepts. And it's always going to be somewhere near someone's house or property. And of course, if you're going to show up and you're going to tell people, oh, we're going to dispose of radioactive waste underground, of course these people are going to have questions and concerns, and you need to properly address these questions and concerns. That's what actually today is all about. And in these two countries, in these two particular examples, they have failed to do so. Because it can be very challenging to explain to people that it is safe to dispose of radioactive waste underground. But there are also examples that show that it can be done. And one example is here in Sweden, where SKB, the Swedish Waste Management Organization, they plan to build a spent fuel repository in Forsmark and a waste encapsulation plant in Oskarshamn. And they have very intensively engaged with these two communities. They have involved them in their plans. And they did in 2013 a survey to see what the local communities thought about these plans. And you can see the results here. You can see that a large majority of the people is actually in favor of these plans. Now, sometimes people say, okay, this is Scandinavia, and Scandinavians are a little bit special in a good way. These are open societies with a culture of debate and consensus, and so they're not representative for the rest of the world. I think it's fair to give the Scandinavians the credit they deserve, but gaining public support for a geological disposal program is absolutely not unique to them. I've shown the examples of Finland and France, but also Switzerland and Canada are making very good progress in actually implementing a geological disposal facility. So to summarize my talk, I hope I have explained to you why storage cannot be a final solution for radioactive waste, because such a solution requires passive safety, which can only be given by a disposal facility. When it comes to the disposal of low and intermediate level waste, these are routinely done all over the world today. That is not the case for geological disposal. That is also that fact that that's not done for geological disposal does not mean that we don't have scientifically and technically sound concept for geological disposal. It is because public participation takes a lot of time and it needs to be done in a careful, slow and stepwise manner. But also there, countries are moving forward in doing this. I've given the example of Canada, Switzerland, France, Sweden and Finland. And with that, I've come to the end of my talk, so thank you for your attention.